Hey everyone, am I audible? Hey everyone, am I audible? Okay, there's a lot of lag, but I think we can work with that. So welcome everyone to ICPC camp session 2, I believe. This session is on FFT mainly, convolutions and FFT. I am going to be discussing lots of problems and giving a brief overview of how FFT works. Uh, I'm Nischay Manwani. I go by the handle EnEm on Codeforces. I have graduated 1 year before and used to be in IIT Guwahati. Now I'm working at Rubrik. And yeah, let's wait for a bit for people to join. Up until then, you can try to solve this problem. This is going to be the main problem that we are going to be solving today. So try to think if you can get to this problem solution. सर एक्सपर्ट 2 मंथ्स में ही कैसे रीच हो गया बहुत मेहनत लगी होगी इन दोज 2 मंथ्स मैन या आई वाज gamified computer programming for those 2 months like I was uh, it was summer holidays I think and I didn't had anything better to do so I was just like you try to grind your skill up in like PUBG or CSGO whatever right I was just grinding in computer programming so I wouldn't say it didn't feel like mehnat to me yeah. Gamer 27 watching now. That's a good number. So feel free to invite anyone that's like want to fresh up on FFT as well. Like this is we do not this stream does not have much prerequisites like first year mathematics like linear algebra, complex numbers, those sort of stuff. Not like there aren't any very big prerequisites outside of that. FFT is mistaken to be a very complex topic because generally all of the FFT questions are in the higher rated range like this. Its range is 2629. So that's why FFT is kind of misconstructed as that. But FFT itself is a very simple topic. So you can understand that and really deepen your like understanding of like mathematics, polynomial multiplication, and divide and conquer. Divide and conquer is also used here, and it's really used in a more very beautiful way, so you can view that. Okay, so today this is the kind of a loose agenda that I'm going to be having today. Like first we are going to be discussing on the problems that we have. Like one is that binomial fever that I just shared with you. Another is like, because this is the ICPC camp, uh, the last like 2021 world final, the Dhaka world final of ICPC also had a really beautiful FFT problem. So I'm also going to be touching upon that, and mainly the polynomial multiplication problem. What's polynomial multiplication? Why we want to multiply two polynomials? I'm going to be touching on that, and I'm going to be giving a brief on DFT and how inverse DFT works. Like these two are the things which enable us to do polynomial multiplication, and entity, how does it differ with DFT, and then we are going to be coming back on the problems, checking how to solve those problems using FFT now, and I'm also going to be sharing like how to exactly see a problem and figure out like this is a polynomial multiplication problem. We have to multiply two polynomials and able to get the answer. So going on to our first problem, which is binomial fever. This has binomial coefficients. Today he came across an interesting problem, but he is currently busy in the kitchen. Can you help chef solve this problem? You're given three integers n, p and r. Calculate the sum s is equal to summation of I is equal to 0 to n p I r, and since the sum could be large, calculate modulo 98244,353. Anybody try to solve any solve this problem? Like any idea that you might have? Ace, I'm just going to be touching lightly on FFT, explain how it works. Mostly we will be dealing it as like a black box to just see like how polynomial multiplication works. We'll be mostly, discussing on the problems which FFT uses. Let me actually share these problems in the general channel as well. If you're in the ICPC Discord channel, or let me see if I can share it in the chat. Yeah, I can share them. This binomial fever. Another one is problem G of last ICPC 2021, and I think this is the last to last ICPC. Let me share that as well. And yeah, these two problems mainly. So for this problem, s is equal to summation of I is equal to 0 to n pi r. This means combination basically. Let us go back to the drawing board and check how we are going to be able to solve this. Summation of I is equal to 0 to n p to the power I r. So we can do instantly some mathematical expansion of it, right? Pi to the power r, let's take this term only and see how this is going to expand. So this is going to be pi minus 1, pi minus 2, and so on by r factorial, right? Nothing confusing about that. This is just NCR. It resolves like this. So basically product of pi minus j, where j varies from 0 to r minus 1 by r factorial. Because this is a summation of all of these terms, This is a special term that we are going to be looking at. Product of pi minus j by r factorial. How we can take the r factorial out. That is going to be constant. We don't have to worry about that. So 1 by r factorial and just summation of I is equal to 0 to n. Product of j is equal to 0 to r minus 1 pi minus j, right? Let's see now. N is 10 to the power 9. We can't do anything in n term. Like we can't go 1 by 1 in the sum term and go by that. I pasted in the YouTube chat, but it isn't showing me. Let me share it in the general chat actually. Give me a second. Just share the problem statement on the general chat. Yeah, it's on the Discord general chat, Kishore, now. So of course we can't do this summation term. The summation term is too large. I minus 1, we can do this, but it doesn't matter because the summation term is too large, right? So we have to extrapolate this term equation a bit more. So what this is going to look like, we can just ignore this 1 by r factorial term now. It's going to matter to us at the last. What I'll do is treat this pi as some x and just try to uh, evaluate what this polynomial is going to look like. If my p to the power I, I'm substituting with some x for some I, right? So product of j equal to 0 to r minus 1 x minus j, right? This I can say as some polynomial of x. Actually p is gonna be confusing, so let me put it as capital P of x, right? This is our capital P of x, the polynomial that we are going to use, and the degree of this polynomial would at max be x into x into x into x up until r times. So this will have a degree of less than equal to r, right? This is our capital Px, the polynomial that we are going to be concerned about. We what this polynomial is going to look like, some a naught x to the power naught plus a1 x to the power 1 and so on so on so on, a r x to the power r. It will probably not have this x to the power 0 term, but it doesn't matter. In that case a naught would just be 0, so we don't have to worry about that, right? So summing up here I is equal to 0 to n is now simpler. Why? Let me show you. This evaluates to, like if we are going to be summing up I is equal to 0 to n for each of these terms, summation of I equal to 0 to n over a to the power 0 p to the power I. We substituted x as pi, right? So summation of I is equal to 0 a to the power 0 p to the power I to the power 0. What's this going to look like? It's just going to look like n into a naught, because p to the power I to the power 0 is 1, right? So it's just summation of I is equal to 0 to n a naught. So it's actually going to be 1 plus n a naught, right? Let's take the second term. That's going to be a1 into summation of I equal to 0 to n x to the power 1. So that's going to be let me, this x to the power 1 is just pi, right? So I is equal to 0 summation to n pi. What's the summation of a gp? This is just a gp summation, right? P to the power 0, then p to the power 1, then p square, then p cube up until p to the power n. Summation of gp is p to the power n plus 1 minus p naught, yeah, p1 minus p naught. This is going to be our second term, and so on and so on and so on. The last term, how the last term is going to look like, summation I is equal to 0 to n ar x to the power r. That is going to be looking like ar summation I is equal to 0 to n p to the power I to the power r. This is also again a GP, right? It's just a GP of the form p0, p to the power r, p2r, p3r, and so on up until pnr. The summation of these terms, it's going to be ar pnr plus r minus 1 by p to the power r minus 1, right? So this whole term reduces to this sort of format that we have now. The only problem is evaluating these AR terms, AR minus 1, A1, A0. We just need to evaluate these coefficients, and then once we can evaluate these coefficients, we can have the final answer easily, right? So just a summary. Let me actually erase everything. Let me just write somewhere else, right? We had the sum I equal to 0 to n p to the power I combination r. What we did was we evaluated this as summation I equal to 0 to n p to the power I, p to the power I minus 1, p to the power I minus 2, and so on up until p to the power I minus r plus 1 by r factorial. We imagined this polynomial to instead be a to the power 0 pi to the power 0 plus a1 pi to the power 1 plus a2 pi to the power 2, and so on up until ar pi to the power r. We substituted this polynomial in the blue circle by this polynomial written in blue at in the black box, right? Once we did that, it was we naturally went to the next step, which is 1 by r factorial. We took this out. We just now have to do summation I equal to 0 to n over all such individual elements here, right? So summation I is 0 to n a0 p to the power I0 plus summation I is equal to 0 to n a1 p to the power I1 plus summation I is equal to 0 to n a2 pi2, and so on up until the last term, whatever that may be. So these terms, because these are GPs that can be easily evaluated, we just need to find out what these a0, a1, a2 up until ar terms are. Once we find that out, once we like find these correct a0 terms, a1 terms, and so on, we can easily substitute this and get the final answer. So any doubt up until now? Am I going too fast, going too slow? You can type into the chat or Discord chat as well. So on. So the only problem that we are left with this in this problem is finding out x minus 1, x minus 2 up until x minus r minus 1. This is in brackets. what does this polynomial evaluate to? What's the like equivalent? A0 x to the power 0 plus a1 x to the power 1 and so on up until a r x to the power r. Yep. So like to evaluate this, we need to multiply these individual polynomials together. This is one polynomial x, just p1 x is equal to x. This is the second polynomial that we have at hand, x minus 1. This is the third polynomial, x minus 2. We need to multiply these polynomials one after the other up until this x minus r minus 1, so that we can get the final polynomial in this form like below, right? These are polynomials right now in this form only. When we multiply x into x minus 1, we can get a polynomial of this, let's call this the nominal form. Like we can get the nominal form of this polynomial like such, x square minus x. So here the a0, a1, a2s are a0 is equal to 0, a1 is equal to minus 1, and a2 is equal to 1, right? Because it is 0 into x to the power 0 minus 1 into x plus 1 into x square. That's the form this polynomial takes. Once we multiply x minus 2, we can get the nominal form of that as well. Multiplying this, we get the nominal form of that. The only problem is multiplying like this one after the other takes a time complexity of big of n square. We can't do that because r is given to be 10 to the power 6, right? So here we need to use FFT. What is FFT? How do we use it? We'll come back to it later. Another problem that you can take a look through, but it won't be like I won't be going through it right now, is this problem. This is uh, the 2021 ICPC World Final at Dhaka G problem. This was solved, I think, like this was the fifth or sixth problem to be solved out of the whole list. Like there were 5 or 6 really easy problems which are solved by like almost everyone, and then the next problem to solve, which was kind of in the middle of really complex and really easy, was this problem. This this also depends a bit on FFT, but it involves a lot other concepts as well. So you can also read that. I've sent the link in the general chat here, and let me go back. Uh, what we are going to be learning today is FFT, or like polynomial multiplication. Let me introduce what polynomial multiplication is first, like the motive behind learning all this. Let me go and write space. So polynomial multiplication is just like digit multiplication. When you are trying to multiply something like 789 multiplied by 23, and you're multiplying by this, you multiply 3 by 987, or whatever those numbers come to be, 1 2 3 4 and so on. 2 into 789, 678, 1, and then you add these up, 1 8 0 1 13 1 2, right? 2 3 0 8 1. It's not the actual answer, I know, but this is the method that you follow to multiply two like integers by themselves, right? Similarly, you have polynomial multiplication, which is just multiplying two polynomials together. If you have a polynomial a of x, which is a naught x naught plus a1 x1, just the nominal form here, a n x to the power n. So this is a n degree polynomial, and then bx, b1 x naught, b naught x naught plus b1 x1, bm x to the power m. This is a m degree polynomial. Once we multiply these two polynomials together, we do the same thing. We write the digits a naught, a1, a2 up until an, and we below that we write b naught, b1 up until bm. We multiply these two together. We take this one, multiply with this whole, write it down here, the first row. We put a cross here to indicate we don't want to multiply again. We take this one. Oh, these 0 to n and 0 to m should be inverted. So there should be m here, m minus 1 here, and there should be a 0 here. Sorry, should be n. It should be n. And this should be m, this should be m minus 1, and this should be 0. Similarly, we take the next one, which is b1, right? b1 would be here. We multiply b1 into a0. This would be b1 into a0. Multiply b1 into a1. That is a b1 a1, and so on. We get the next row, and so on and so on. We compute the whole thing. We add each column up. In here, while adding each column up, we don't take carryover. Even while multiplying at the top level, right? We don't take carryovers. That's the only difference between normal integer multiplication and polynomial multiplication. In polynomial multiplication, there are no carryovers, and we just add it up here directly without any carryovers. So let's say there is an 8 here and there's a 9 here. We add them up as 17 directly. And what the 17 indicates? 17 here indicates that there should be a 17 x plus whatever a naught b naught comes out of here, a naught b naught x to the power 0, right? This makes sense how we used to do polynomial multiplication normally as well. If you have like a naught x plus a1 x plus a naught and b1 x plus b naught, when you open this up, it becomes a1 b1 x square plus a1 b naught plus a naught b1 x plus a naught b naught, right? So this is the final polynomial 0 term. This is the final polynomial first term. This is the final polynomial second terms. That's what we are doing here as well, right? This whole process, however, takes big O of n into n time, because we need to multiply this with this whole thing. That takes big O of n time. We multiply this with the whole thing. That takes big O of n time, and so on and so on and so on. We take this term and multiply with the whole thing. That takes big O of n time as well. And then the final additions of all these things also takes big O of n time, n into m time. So this is too much. We can't use this even in like computer architecture where you are, because this polynomial multiplication is directly used to multiply two integers as well. So in computer architecture, whenever you're trying to multiply two polynomials, right? In C++, when you write 6 into 7, it's not actually multiplying in this fashion. It doesn't have code like this. It actually has coded it up using FFT. So as to reduce the time complexity. What's the time complexity of FFT? It's going to be reduced to, I'll give you a spoiler, it's going to be reduced to big O of n log n. Or like in this case, it's going to be reduced to big O of n plus m log of n plus m, right? So how do we reduce it to this? It goes through a complex fashion of reducing it. So I'll just brief you on that, and later we are going to be using it as a black box. Okay. Let me go here. Yep. So how FFT works? This was our polynomial ax. We needed to multiply it with the polynomial bx, right? Directly going it like this way to get the polynomial, let's say the product polynomial is cx. This takes big O of nm time, right? But there is another way to multiply two polynomials. What if, let's say, I've given you like let's say I've given you exactly n plus m points, or n plus m points of like what's the value of x of those n plus m points. I've given you n plus m coordinates. I think this would be simpler to imagine. N plus m coordinates of ax and bx. So let's say I've given you what's the value of 1 of a1, This is the first coordinate. Second coordinate is 2a2. Third coordinate doesn't need to be like 1 2 3 so on. It can be like 78 8 78 and so on. There are n plus m coordinates like this here, and on the same values here 1 2 78 whatever those values may be, we are also given the values of bx. So 1 comma b1, 2 comma b2, 78 comma b78, and so on. These values we have given here, right? Can we extrapolate the value of can we extrapolate the polynomial a using just these values, these n plus m values? The answer is yes, because uh, you might remember in your high school classes, to uniquely determine a polynomial, we need a certain number of points of that polynomial, which is exactly equal to the degree or degree plus 1. I don't remember exactly. So let me just take an example, right? If we have the polynomial x square minus x plus 1, right? How is this going to polynomial look like? At 0 it has the coordinate of 1. At 1 it has a coordinate of 1 as well, and I think it would have a, so this is our polynomial, right? Something like this. I've drawn a very bad parabola, but bear with me. So this is our polynomial. This is how the polynomial is going to look like. So let's we know the value of 0 of it. 0 comma 1 we have this value. We also have the value at 1. So 1 comma 1 we have that value. I think we also need a third value. So let's get the value at 2. 2 square 4 minus 2 plus 1, 2 comma 3. Now when we have these three coordinates, right, and we don't know anything about this polynomial, let's pretend that we never knew about this polynomial. We only have these three coordinates, and we are given that it is a polynomial of degree 2. We need to find that polynomial. We can exactly find out which polynomial we had in the beginning using only these coordinates, right? We just need to do three, like we have three variables sort of. Let's imagine the initial polynomial was a naught x, a2x square plus a1x plus a naught. So we put these three coordinates in here. So a2 0 plus a1 0 plus a naught is equal to 1. So from this equation we get that a naught is equal to 1, right? Then the next equation we have a2 into 1 plus a1 into 1 plus a naught is equal to 1. We know a naught is equal to 1, so we get another equation that a2 plus a1 is equal to 0. Just the last equation we have a2 4 plus a1 2 plus a naught is equal to 3. And now using these two equations, or these three equations rather, we can get like what were the initial values of a naught, a1 and a2 were. These are just linear system equations. So we need degree plus 1 coordinates to find out what the initial polynomial was. So how much coordinates are we going to need to find out the exact polynomial cx, the cx polynomial? This cx polynomial, because we are multiplying two polynomials of degree n into m, right? This is degree n and this is degree m. What is the degree of this polynomial going to be? It's going to be exactly n plus m, right? The final value, which is going to be cnn plus m, x to the power n plus m, that is just going to be an xn into bm xm, right? So this is going to be having a degree of n plus m. So we actually need I wrote incorrectly here. We need n plus m plus 1 coordinates, right? So because we were calling this form of the polynomial as canonical form, I think, sorry, nominal form, right? We're calling this form of the polynomial a naught x naught plus a1 x1 up until this is the nominal form of the equation, nominal form of the polynomial, right? Now we are going to be dealing with another form of the polynomial, of the same polynomial. This another form is this kind of form where we have exactly on some values, let these values be v1, v2 up until vn plus m plus 1, we have the exact value of this polynomial, like what's this polynomial going to be at that value. So a of v1, a of v2, and so on up until a of v of n plus m plus 1, right? So if we have this list of values here, let's call this list of values as this was the nominal form, let's call this as representation form, right? So if we have the representation form of polynomial a and we have the representation form of polynomial b, can we get the representation form of polynomial c? Yes, and that is quite easy. What I'm talking about is if we have a of v1, a of v2, and so on up until whatever, and b of v1 and b of v2 and up until whatever, can we get what is going to be cv1? Yep, that's just multiply these two, that's going to be this, right? At v1 value, polynomial a had this value. Let's say v1 is 1, right? And a v1 was 5, and let's say v1 is 1, this was a1, and like b1 was 10, so c1 is just going to be 50. We just have to multiply these two values together and we get the value of c, and that's logical as well, like we are just multiplying two polynomials together. What does this polynomial signify? That at each point the product of this like the individual values of this polynomial should be equal to the value of the product polynomial, right? Similarly, we are going to be multiplying these two to just get c of v2 and so on, right? So multiplying two polynomials in their representation form is really easy, and it takes big O of n plus m time, right? So these polynomials are in nominal form. This is a nominal form. This is a nominal form. This is a nominal form. If we are going to be multiplying them in nominal form, it takes big O of n of m time. But if we have these polynomials in, let's say, in their representation form, this is in representation form, and this is in representation form, and this is also in representation form, then this is going to take just big O of n plus m time, right? So the only problem remaining is how to convert this nominal form to the representation, this nominal to representation, and how to get the nominal form back from the representation form for cx. If we can do these two and these two in big O of n plus m log of n plus m time, then we have our FFT equation, and that FFT works like this. So any doubt up until now? You can put it in the chat. I'm looking at the chat constantly, so you can. So this conversion from here to here, right? This is actually a bit convoluted. I'm going to give you the overview idea, right, of how this nominal form to representation form works in the representation to nominal. There are some certain points, but like if you want to read in detail, I I would recommend to go to the CP algorithms page of it and read that directly, because it's a lot more involved there. But the main points are, uh, the representation form we are not going to be doing in 1 2, or like these aren't going to be going to be our values. The values are specifically going to be omega naught 0 n, omega 1 n, or whatever. What this means is this is a complex nth root of 1 to the power 0. So what this means, like if you have the equation, uh, if you have the equation x to the power n is equal to 1, this has n complex roots, right? Let's take a non-trivial root of it, right? So the one which is like makes the least angle with the real number line, right? Whichever makes the least angle with the real number line. Here is 1, here is omega 1 n, and then this is going to be omega square n, right? Just the one after it, 2 theta at 2 theta angle. Then at 3 theta angle we will have omega cube n, and so on and so forth, so forth. At this we have omega n by 2 n, which is just going to be minus 1, and so on and so forth, so forth. So we are going to be calculating the representation form at these values. Our v1 is going to be this, v2 is going to be this, and so on. And the second point is we utilize divide and conquer, but not in the way you think. If we have the polynomial ax as a naught x naught plus a1 x1 and so on, we divide this polynomial into to do divide and conquer, but we divide it as a naught x naught plus a2 x2 plus a4 x4 and so on, all the even terms, and a1 x1 plus a3 x3 plus a5 x5 and so on, all the rest of the terms. If you are interested, do read about it. I find the FFT algorithm to be really, like there is a reason it's the most talked about algorithm on the planet. It's really interesting to read about it. So like I'm going to be giving the link where you can read about it. This is the one that I read about it, but I think Veritasium has a new video about it. It might not be that informational, but if you just want to dip into it, you can read that as well, watch that as well. But if you want to go in depth and specifically about computer programming, you can go here, right? And it comes in use in computer programming as well. It's not like you can just uh, use FFT as a black box and get away with it. In 90% of the problems you can, but in those 10% of the problems where you might need to, like not do polynomial multiplication but polynomial exponentiation, at that point you really need to know like how exactly the insights of the FFT algorithm works. Yep, this is the implementation. You can pick up the implementation from here as well. This is a very non good implementation, like it's really high latency, so you can probably use the implementation I use, or like you can find many better implementation on the net as well. And yeah, one more thing finally on the FFT topic. Most of the times we don't use actual FFT, which involves its complex numbers. We use NTT, which is numeric theoretic transform, because complex numbers involving complex numbers means there is going to be floating point arithmetic, and that is going to have a lot of caveats with it. It's going to basically put like approximation. The word I'm looking for is like the integers are not going to be exact anymore. There's a chance that the integer is not what you wanted, is -1 or +1 now, right? So to have exact FFT be working, we do entity instead of using those complex roots that I was talking about before, omega 0 1 omega 1 n and so on. We use the roots of x to the power n equal to 1. We are going to be using the roots of that. That's not going to change. but now this is going to be mod of m, whatever mod of m is given there, right? So like in this problem, we were given mod 998244353. So if you want to find out like what are the roots of x to the power n is equal to 1 in 998244353, there are, I think, 2 to the power 23 roots of this equation in this, right? There are 2 to the power 23 roots uh, of x to the power n. Oh yeah, what does this n signify? Whatever the n you want to put. So this 2 to the power 23 roots actually, let me make it a bit more sense. So x to the power 2 to the power 23 is equal to 1 has roots as like roots that you can use. X to the power 2 to the power 24 is equal to 1 will also have only 2 to the power 23 roots. It wouldn't have 2 to the power 24 roots. It would have only 2 to the power 23 roots. So this is to say that we can apply FFT on an array as big a size of 2 to the power 23, which is around 8 into 10 power 6. So we can apply FFT on an array as big as 8 into 10 to the power 6 if we are given that the modulo number is 998244353. This is a special number. We can't apply it with every other number. This is a special number, and you'll have to read like how exactly is it special on here as well. The exact functioning of how that works is here. Like if you pick up a prime number randomly, it should be of the form c to the power 2k plus 1, and whatever this k value we have, this k value should be the highest. If this k value is like 20, then we can use 2 to the power 20 size array in our FFT, like that. Coming back to our problem, how are we going to be solving that problem? Which was this one, right? So now we have FFT in our tool, right? Let's treat FFT as a black box now. Let me erase this. So imagine FFT here, right? You send in two polynomials ax and bx, and out comes a polynomial cx in time complexity big of n log n time, right? So if you try to do that here, if you have multiplied this polynomial with this polynomial, you'll get the second degree polynomial in n log n time. That's fine. If you multiply that with this, that's fine, and that's fine. But if you multiply, like, let's say you have a polynomial of size I in between, and you multiply that with x minus I or whatever, right? That's going to take you I log I time, right? If you add this I log I for summation I equal to 0 to n, that's going to come to big of n square log n time. So we are kind of regressed here. We were taking big of n square time before, and now we are taking big of n square log n time. So how do we improve on this? We actually have to do divide and conquer. This is not the type of divide and conquer we used in FFT. This is a simple type of divide and conquer. We just divide the equations in half, calculate the left half, calculate the right half, and then multiply them together, right? So what do I mean by that? Multiply x minus 1, x minus 2, and so on up until x minus r by 2, and then x minus r by 2 minus 1, and so on up until x minus r plus 1, right? Let's put a separator in between. Multiply this recursively, multiply this recursively, Both of these are going to take let's say the total time it takes to multiply this whole thing takes t of r time, right? So multiplying this is going to take t of r by 2 time. This is going to take t of r by 2 time, right? So our t of r is nothing but 2 of t of r by 2. And how much degree this polynomial is going to be? This is going to be around r by 2 degree polynomial. This is also going to be around r by 2 degree polynomial. So multiplying these two polynomials which are coming out, which are both of degree r by 2, is going to take us big O of r log r time. You can use Master's algorithm and you get t of r as big O of r log square r time. So this is the final way in which we have to solve this problem, which was binomial fever. We first convert this sum form into like a polynomial form as we did above. Yep. Summation of I equal to 0 to n pi of r, right? We basically opened up this pi by r like combination term as pi into pi minus 1 pi minus 2 up until pi minus r plus 1 by r factorial, summation of I equal to 0 to n. This r factorial we can take out. We are just going to be ignoring that, just going to be multiplying at the end. This is going to be taking big of r time. We don't worry about this small term, but we have to worry about this big term. What we did, we substituted this with a0 pi0 plus a1 pi1 plus a2 pi2 up until ar pir, right? Basically substituted p to the power I as x, so we get x minus 1 x minus 2 and so on up until x minus r plus 1, and basically opened up all of the brackets to get a to the power x to the power 0 plus a1 x to the power 1 and ar x to the power r, right? Once we get this form a0 x to the power 0 etc., to get this form we have to apply FFT with divide and conquer, like I explained below. You multiply this x minus 1 recursively, you multiply this x minus r by 2 minus 1 about x minus r plus 1 recursively, and then you multiply whatever polynomial you get on the left hand side and the polynomial you get on the right hand side using FFT as a black box here, right? And once you do that, you get this form, and then it's just a simple GP sum that you want to get. I is equal to 0 to n pi to the power 0 or summation I 0 to n pi I1. This is a simple GP where you are adding p0 plus p1 plus p2 up until p to the power r. So that can be done like using a formula like the GP sum formula that you know. Yep. This was all of the things that were required from this problem. I don't think I was able to solve this in contest. Let me check. Yeah, I probably wouldn't have. This was the last. Where's the expand contest code? Oh, it was a long challenge problem. Okay, then I might have a partial. Okay. Yep, lots of people got the full one. Mine probably failed because it was very slow. Then yep, I was utilizing FFT and all those correct things, but I was using my own FFT. I shouldn't have used this. This like my implementation of FFT is really slow. That's why I'm telling you to pick up like an online implementation as well, like which is going to be fast. Like my implementation is really slow in that case. So that's why I got a like time limit exceed. But yeah, there are people who got this in the contest as well. You can check their codes out. I'd recommend TMW William. His codes generally uh, are a bit better to look at. Yeah, his entity implementation is really good. You can you can pick this entity implementation directly and use this. And finally, you solved it. Yeah, you can check this solution out. Moving on to our second problem, which is international center. So this was a ICPC problem. This doesn't depend a lot on FFT, but yeah, I'm going to be basically using this problem to tell, like, it can be like FFT is a really small sub problem in the problem as well, right? So let me first detail this problem, what this problem is about. So we have a motif and a mosaic. Like, the left hand side of this image is the motif and the right hand side is a mosaic. What this motif is just a pattern that we are trying to find at this mosaic. Think of it as string pattern searching, right? We are trying to find some substring in a big string. You might have heard this problem already, where you use KMP or hashing or stuff like that, right? So in those kind so there this motif is our pattern and the mosaic is our like the string that we are trying to find the pattern in, right? uh, the mosaic would have some colors. Let me actually read the problem as well. International Center for Preservation of Ceramics, ICPC, is searching for motifs in some Asian mosaics. Mosaic is a rectangular grid where each grid square contains a colored tile. Every tile would contain a colored tile. A motif is similar to a mosaic, but some of the grid squares can be empty. So this is a string pattern matching problem, but we have wildcards as well, where the grid squares can be empty and it can be matched with any one of the color tiles. We don't give a shit there. Figure G1 shows an example motif in mosaic. G1 left and mosaic right. The rows of RQ into CQ mosaic are numbered from 1 to R, top to bottom, and the columns are numbered 1 to CQ from left to right. Contiguous, this is just the definition of how we are going to be matching it. Basically, if this matches at this point, let me actually draw it here. It's going to be better to understand. This box, which is our pattern, matches this box because this red part matches here and this red part matches here. This is empty, so it can match with anything, and this is also empty, so it can match with anything. It also matches with this box, again for the same reasons, and it also matches with this box, again for the same reason, right? So that's just, it has basically detailed the definition here. And given the full motif and mosaic, find all occurrences of the motif in the mosaic. We just have to find all of the occurrences where this is happening. Input 1000 and the colors can be 0 to 100. Again, the mosaic also has like rows 1000 to 1000. A value of 0 denotes an empty square in the motif, and the colors can be 1 to 100. Here it can be a 0 to 100, 0 denoting the empty square. Output, you have to output k lines, all of the k matches where it happens. And for the first example that we saw above, this is our motif, this is our mosaic, it matches this part, so we output 1 1. This also matches this part and this part, so you output 1 3, and also matches this box, so we output 2 2, right? Simple problem. What we are going to be doing for now, we are just going to be thinking about the 1D part of this problem. Let's think that our pattern and the motif and mosaic both are 1D. Also, let's get rid of the motif and mosaic terminology because it's very hard to say. So pattern and string, right? We are going to be, and these colors, instead of these colors we have characters, and then we have the wildcard, which is a question mark, which is the empty tile, right? So what I'm saying is, let me go back to the dashboard. mm, let's say we have a pattern like a n comma, right, and we have a string as banana. We need to find this pattern in this string where question is our wildcard, right? So where does it match? At this place a n question mark, and at this place a n question mark. So we output 2 and 1 2 3 4, yeah, 4. We output 2 and 4. That's basically the question. You can extrapolate it to 2D as well, and then you will finally solve the final problem. But this is basically what the our problems boils down to, right? So to solve this problem, your immediate thought might be KMP, right? Like if you had a complete string instead of the wildcard, it's directly KMP. You don't have to worry about anything else. It's just string pattern matching, where there are like thousands and thousands of blogs online where you can read upon KMP or string pattern matching, right? There might be one here as well. String processing and string hashing, grab and carve for string matching. This is the hashing one that we use, and there is also, there should be a KMP here, huh? We don't have KMP on CP algo, but you do have on GFG, I'm sure. Yeah, KMP algorithm for pattern matching. The only twist here is we have this wildcard, right? Now there might be other ways to solve this problem as well, but the one I used was the FFT problem, FFT way, right? So how does that work? It like first we have to basically think in terms of hashing, right? uh, and we also have to think in term of character by character. So what we are going to do, is there by full name, okay Kishore. But yeah, so what are we going to do in this problem? We are going to be thinking in terms of character by character instead of uh, having it like trying to find a whole pattern in the whole string at like one time, right? This is not going to be really increasing a time complexity a lot, because in the problem we saw that the total number of colors are 100. So like it would increase whatever like complexity we had by 100, which is not going to be a lot, might be a lot, we'll see at the end. But uh, yeah, we'll start by character, right? So what I'm trying to say is I want to check where this pattern, right, directly from this question, from this pattern a question mark, where does this pattern lie in some star. We don't care about b, right now we only care about a star, a star, a, where this pattern lies in this string. At what steps does it lie? If we can find that out, right, we'll like let's try run that. We get 2 and 4, right? Also when we try to find out where does question mark and question mark lies in the string star star n star n star, where does this lie, right? And we also find out it lies at 2 and 4, and because this 2 and 2 matches for each character, we can definitely say that okay, 2 is one occurrence where our whole pattern is matching the whole string, right? So 2 is one valid matching, and 4 is also one valid matching because 4 matches in both of the characters. So the thing we have remaining is we have some special character, right? In this problem we were thinking about the character a. In this problem we were thinking about the character n. So let's take this special character as c, right? And then we have some wildcards, question mark c, question mark whatever, question mark c, right? This is our pattern, whatever pattern we have. Where does this pattern lie in the string s? And the string s looks like some stars, which are some characters apart from c. Except for c, we have just blanked out all the characters because we do not care about them. So star star star, c star star, c star, and whatever whatever. This is our whole s. We just want to find out when does this pattern along with wildcard matches in this string s at what points. To do that, what I did, there might be really, now I'm looking at this problem formally defined, I feel like there might be better ways to solve this. But what I did was, I constructed a polynomial a naught, x naught. Let me be a bit more clear on this. Give me a sec. So at whatever, I constructed a polynomial of this form, 1 into x naught plus 0 into x1 plus 0 into x2 and so on. Sorry, 1 into x3 plus 0 into x4 and so on up until 0 into x to the power n minus 1 plus 1 into x to the power n. So at whatever places we have the character, right, I put a 1, and whatever places I don't have the character, I put a 0. At this place I put a 1, at this place I put a 0 and 0 and 1. Similarly, I construct a polynomial for the second string as well, which is 0 x0 plus 0 x1 plus 0 x2 plus 1 x3 plus 0 x4 plus 0 x5 plus 1 x6 plus 0 x7 and so on up until x to the power m, whatever 0 or 1 there might be, right? These are the two polynomials that we have, and I'm also going to be reversing this polynomial. So instead of having this, I'm going to be reversing it. So it's 0 1 x to the power 0 plus whatever, and then we start from here, 0 x to the power m minus 7 plus 1 x to the power m minus 6. So I'm basically putting this 0 as here, this 1 as x m to the power m minus 6 coefficients rather than the 6th coefficient, and this 0 is going to come as x to the power m minus 5 and so on up until we get 0 to the power x to the power m, right? So I just reversed this polynomial and I constructed this polynomial. Now I'm going to be multiplying these two polynomials together, and let's say the final polynomial looks like this, 1 x to the power 0 plus 5x to the power 1 plus 3x to the power 2 and so on up until some a n plus m x to the power n plus m, right? At whichever places we have the value ai is equal to the number of ones in polynomial of p. At the count of values we have this, right, that is going to be our answer. How? I'm going to display a bit. So what we are doing here is I'm multiplying this polynomial with the reverse of this polynomial. What's its 0th term going to look like, right? Let me show you what the 0th term of this is going to be look like. Let me write this in a proper form though. This polynomial that I was talking about the pattern polynomial, right? Let me write it as p0 x0 plus p1 x1 is just this polynomial that I was mentioning about here. I'm just writing it in the proper way. p0 x0 plus p1 x1 plus p2 x2 and so on up until Pn x to the power n, right? This P1 denotes 0 if wildcard at I, else 1, right? Similarly, we have the string polynomial, the reverse string polynomial, s0 x0 plus s1 x1 plus s2 x2 up until sm xm. Here, this si is 0 if s, the initial string, has n m minus 1 minus I as wildcard, or the any other character that we don't care about, else it's going to be 1, right? This is just the polynomial that I've constructed here. I'm writing it in this form, like to basically denote that I also reversed this polynomial that I constructed. So the product of these two polynomials, 0th term, is going to look like this: p0 into s0. Nothing much, right? P0 into s0, we don't care about that. But let's look at the nth, yeah, the nth coefficient. The nth coefficient is going to look like Pn s0 plus Pn minus 1 s1 plus Pn minus 2 s2 and so on, P0 s to the power n, right? Its value is going to be the number of times there was a character, there was C at this ith position, like the ith positions I mentioned here, right? If this is 0 and this is 1, this value is going to come out as 0, right? Because 0 into 1 is 0. If this was 1 and this was 0, this value is also going to be coming out as 0, right? And this does mean that our pattern string is not matching up with our actual string, because there was a C in this pattern at this n minus 1st position, but there was not a corresponding C at in the string, right? Only if it was a 1 and a 1, at that point we are going to be resulting at a 1, and this coefficient, which is the nth coefficient of the string, is just going to be adding up all those ones that we are collected, right? If this value is exactly equal to the number of ones in our initial polynomial, which is this polynomial, let's count the number of ones that we had in this polynomial, and let's say that value as t, right? If this exact value is going to come out as t, if this is t, then that means we had a match at nth position. Why? Because this Sn corresponds to, in the string, it corresponds to m minus 1 minus nth position, and this S0 corresponds to m minus 1th position. Sorry, so it wouldn't be at the nth position, it would actually be at m minus nth position. Yeah, m minus nth position. Like similarly, if we go at the n plus 1th position, the polynomial would still multiply these stuff. If the value is coming out to be exactly t, then we also had a match at m minus n minus 1th position, and again the next coefficient we check that if that is also coming out to be the exact value t, we had a match of m minus n minus 2th position, and so on. This is going to happen in like big O of m plus n time. Don't worry about that. This multiplication is also going to happen in big O of m plus n log m plus n times, so we don't worry about that either. Yeah, and together with this we are also going to be doing this for each of the character. As I said initially, we are going to be doing this for each character that we have in our pattern. So for A we are going to be doing it once, for N we are going to be doing it once. So this we kind of will be doing 100 times in the initial problem, or the number of characters we have, right? So this is going to be our final complexity, which is not going to be a lot, as we also have the time complexity of time limit of 6 seconds. So 1000 into 1000 into log of 1000 into 1000. So the final complexity will look like something like 10 to the power 6 log of 10 to the power 6 into 100, which is 10 to the power 6 log comes out around 20, right? Yeah, 20 into 10 to the power 8, so 2 into 10 to the power 9. This might seem a lot, but because the time complexity is 6 seconds, it's going to work. Sorry, time limit is 6 seconds. Yep, this was like one of the problems, like kind of in the middle in the ICPC World Final. But it really is going up until this level, like once you start working with FFT and you have experience with it a bit, I think this step right here, which I took to evaluate like at what positions do we have a match, to gen to generate one polynomial out of this string and to generate another polynomial out of this actual string that we are trying to find a pattern in. These two steps are uh, going to be intuitive a bit. Uh, you'll learn how to find the polynomials that you want to find in your problems, right? And once you have those polynomials and you can multiply, the only tough thing is to like actually get to this form, which was a bit hard, I would agree, to basically do it character by character instead of like having it a whole pattern and trying to find the pattern as a whole. But yeah, this was the problem that I talked about. Another one that I really want to talk about is this. How much time do we have? Let me check. Okay, we have been streaming for 77 minutes. Alright, I'll just take a 10-minute on this idea as well, and then we'll be closing our stream. So this exact I'll send the link to this in the general chat as well, so that you can look at it later. But this is a really nice idea that I found like some time back when I was like actually doing computer programming. The actual problem being discussed here is nonsense. You don't need to worry about that. You are supposed to count the number of corrected undirected label graph with n vertices algorithm with n log square and time complexity. Don't worry about this, right? They are trying to find out something, the number of connected undirected label graphs. The thing that we are going to be worrying about is trying to find this equation. Fn is equal to gn minus n minus 1 summation of m is equal to 1 to n minus 1 combination of n minus 1 of m minus 1 into fm into gn of minus m, right? This is a dp equation, and I'll even like simplify it a bit more, right? Instead of this, let's write it as dp of I is equal to summation of j is equal to 0 to I minus 1 dpj into a of I minus 1 minus j. Right? I simplified this a lot. This doesn't actually correspond to this value at all, but like this is the essence of what we are trying to solve here. Let me write this in the whiteboard actually. dp of I is equal to summation of j equal to 0 to I minus 1 dp of j into a of I minus 1 minus j. So basically what you're doing is you already have dp0 values, and these a values are constant, or you can like trivially generate them. These are not hard to generate, right? These are trivial to generate. uh, you want to calculate this whole table of dp, right? You have dp0, that is a constant, the base condition, whatever you given that, right? And now you're trying to calculate dp1, that depends on dp0, and its exact value is dp0 into a0, right? The next value you want to be calculating is dp2, and that you can calculate as dp1 into a0 plus dp0 into a1. And similarly, as you go down, when you get to dpi, that is dpi minus 1 into a0 plus dpi minus 2 into a1, and so on, right? So this kind of form of dp like appeared a lot for me during when I was doing computer programming, and like as you can see from the dp, like it seems kind of intuitive that you have to calculate it one by one. You can't like jump from dp1 to dp3, or you can calculate dp2 to dp3 together. Like you have to first calculate dp1, only then you can calculate dp2, and then you have to calculate dp2, only then you can calculate dp3, and so on and so on and so on. You can only calculate dpi once you have calculated dpi minus 1, and you also can't pre-calculate this part as well, because dpi minus 2 into a1 you haven't really multiplied any time before. You haven't even multiplied what's the last term here, dp0 into a of I minus 1, right? dp0 into a of I minus 1, you haven't multiplied these two values together at any point before. You have multiplied dp0 into a0, you have multiplied dp1 into a0, you haven't multiplied dp0 into a of I minus 1. So it seems like you anyways have to do n square multiplications here. You have to do this one multiplication, this one multiplication, this one multiplication, and at each row you're getting like here you have to do 5, you have to do 6, 7, 8. So anyways you have to do n square multiplications. So there is no way you can calculate this whole dp table in less than big of n square, right? That's very wrong. Like it was like an epiphany to me, like you can actually do that, and this whole page kind of details how you do that, and it's a little bit complex here, so I'm just going to be explaining here. It of course utilizes FFT, and it utilizes divide and conquer as well. How it utilizes divide and conquer? Yeah, the time complexity finally comes out to be big of n log square n, and it does that by first, if you want to calculate like let's say dp0 up until dpn, right? You calculate up until dpn by 2, you calculate this first, and you calculate these terms afterwards, right? Let's say you have recursively calculated this, recursively calculated this down part, right? When you get to this part, you have to do one operation in between, such that the products of all these terms dp0 up until dpn by 2, whatever like dependencies these terms have on these term, right? Whatever dependencies these have, all dependencies, you can calculate in big of n log n time using polynomial multiplication. you just have to construct two polynomials, one polynomial of a0 up until an, and one polynomial of whatever dp0 terms you have calculated here, right? And you have to order them in such a way such that those make sense, and then you have to multiply them, and then you have to pick up the exact coefficients and you have to put them here, right? Such that that also makes sense. But once you do all these calculate all these dependencies and calculate them, then you can go on and calculate this recursively as well. As you have taken care of all of the dependencies this has on this can be now done in isolation, right? This recursion can be done in isolation, where you only have to worry about like let's say dpn's dependency on these values, and you don't have to worry about dpn's dependency on these values. And this can be calculated in t of n by 2 times as well. So you have the same equation that we had some time before. T of n is equal to t of 2 into t of n by 2 time plus big O of n log n, which by master algorithms becomes t of n is equal to big O of n log square n. The only thing remaining is how do we do this multiplication. That's a bit involved and a bit complex as well. Yeah, so it basically has two ways. First, you have to construct this polynomial, which is fn is equal to a naught x naught plus a1 x1 and so on up until a n xn. And then the second part, where you have to calculate gx, and most of the times you actually reverse the second polynomial. That is most of the times how polynomial multiplication, like competitive programming problems on polynomial multiplication works. There might be problems where you don't actually reverse the second polynomial, but in this problem as well, I can intuitively see I'll have to reverse this, right? So I'll reverse this first hand. So dp n by 2 x to the power 0 plus dp n by 2 minus 1 x to the power 1 and so on up until dp0 x to the power n by 2, right? Once you multiply these two polynomials, let's say you get the polynomial f into g, you get hx, right? Which is some h naught x naught plus h1 x1 up until h n plus n by 2 x n plus n by 2, right? What does a random coefficient, some let's say hi to the power xi we have in between, right? What does this indicate? We have hi is equal to that would be a naught into dpi plus a1 into dpi minus 1. Oh no, because I had actually reversed the second polynomial, right? Oh, I don't think I needed to reverse the second polynomial actually. Give me a sec. Did I? Oh no, I didn't. Okay. So yeah, in this case, like I said, there might arise some cases where you don't have to actually reverse your polynomial. So that is one such case, you don't have to. So this is dp0, this is dp1, this is dpn by 2, just directly, right? So this comes out to be a naught into dpi plus a1 into dpi minus 1 plus a2 of dp of I minus 2 and so on up until a of I dp dp0. Yep. So this can be directly added in this dpi term that we have in the second half. In the second half we'll probably have a dpi term right? DPI term, and what, like how we describe the DPI term above, such as dpi minus 1 into a0 plus dpi minus 2 a1. So sorry, actually not dpi term, the result that we got below would be added into dpi plus 1, right? So in dpi plus 1, we can directly add this value that we got here, we can add in here whatever this value had before. We'll initialize all the dp's with 0, right? First it will be 0, and then we'll add this value that we got into this dpi plus 1, and now the dependency of the left hand side is resolved in dpi plus 1. In dpi plus 1, we don't need to ever consider the left hand side dp values ever again. We just need to consider the right hand side values. So this is how this linear FFT tricks, man, linear FFT trick works for DP. So using FFT to speed up DP. This is also again a very beautiful thing that you can use. More things that you can discover in FFT, mainly in convolutions. There is one thing called FWHT, which is basically said that it's the next thing that you're going to be working on, reading on if you have completed FFT. But frankly, I've never used this, really never used this. The one time that I used this was like an internal IITG competition where some senior was really interested about FWHT, so he put it in a competition, and that's why I had to use this. But I don't think you'll ever need this. The more important thing you'll need is to learn how to do this kind of convolutions, right? How to basically extract the polynomials out of the problem that you're working with. So for that, practice, go to Code Forces, go to the FFT tag and do all the problems that you can see. There is also one more like really novel thing that I can probably provide you. I'm not sure if I would have the link handy to it right now, but basically in subsequent lectures you might be reading about combinatorics, right? So in combinatorics there is something known as Stirling numbers, right? Stirling numbers of first kind, Stirling number of second kind, Bell numbers, so on and so forth. There is a lot of kind of numbers in like combinatorics. So in the Stirling number of first kind, you can use FFT to calculate this as well, and this is a really novel technique to use to calculate the Stirling number of first kind. Let me try to find a link actually. June, not the convex trick, not binomial fever, faulty generation. Probably not in study as well. I'll try to find a link to it, but there is a really novel technique through which you can calculate the Stirling number of first kind using convolution in big of n log n time. It's trivial to calculate it in big of n log square n time. You just use a divide and conquer with FFT like I've told you in this lecture, but there's a really novel technique to calculate in n of n log n time as well. And the Stirling number of second kind, that can only be calculated in that can be calculated in n of n log n times as well. Okay, so both of these numbers can be calculated in n log n time, if I remember correctly. Yep, both can be calculated in n log n times, and one of these is trivial, one of this is a really novel technique to use, and together, once you have this in hand, right, you can also actually calculate any factorial, n factorial, in big of root n log cube n times time complexity. Generally n factorial takes like big of n times only. In 99.9% of the problems that you solve, you're going to need just the big of n time complexity and factorial. But like it's very interesting to read about this one as well, where you can basically do it in like square root of n times instead of big of n times. You'll never need this in an actual competition, but yeah, it can be done. I'll also try to find the link to this one and the Sterling number of first kind. And if I did do found one, I'll send it in the Discord chat that we have. Yep, that's it from me for FFT and convolutions. And yep, Kishore, any ending words that you might have? You can jump in and say anything if you want. Assuming you are listening it to this right now. Oh, Pramod, sorry, I missed the chat. Is there any way of modifying the 1D string matching algorithm to account for the wildcards, also representing no character, like in regex, for example? I don't understand your problem exactly, Pramod. Like in regex, we use no character, also representing no character. We in regex, what I remember, we have like only question mark and star. Are you talking about the star regex, where you match any number of characters? Let's say we have a b star. This matches with a c c c c b. Are you talking about this character, Pramod, by any chance? No, right? Like here the
Probably means
wildcard
like
character means any character, right? Can we modify it to say any character plus lack of character, meaning a question mark a can match with a as well as aba? No, I don't think, Pramod. Like uh, the algorithm that I showed you, that can't be modified easily to match with that. I don't think it's going to be can be modified in any way to work with that. That's a really complex problem, and probably I think the novel solutions to it might just be like might just not be like sub quadratic, like n log n or something. It might be n square or larger. Anyways, if you have more questions, you can jump in the chat. I will be in the Discord chat for a few seconds. Uh, Here, this general voice chat, so you can jump in and yeah. Hey Kishore.
hello. There is heavy delay. Okay, I'm muting the actual video because
Yeah,
it's
mute that video. Yeah, yeah.
yeah. Thanks a lot for taking the meet. The last part is really cool. I need to still figure out what you're doing there, but
Hmm,
that was really nice. Yeah.
hmm,
Thank you for taking the meet.
hmm.
And yeah,
Yeah.
I'll if you're gonna post a VJudge or like if you have any cool problems, just send them over. I'll put like a small VJudge or something on the Discord server and the
On the
links.
Discord server, right? Right here.
Uh, Yeah, should just send me the problem links. I guess I'll make a small VJudge out of it or something like that.
Uh,
I'll
okay.
post
I
it.
have all problem links. Okay. Yeah, I'll try to find some.
Yeah,
I hadn't
yeah,
worked on it before.
yeah.
Hey Kishore, I guess you haven't muted the stream. I mean, it's still going on the stream. Whatever you're talking.
Yeah. Okay. I can close the stream now. Okay.
Sure.
Okay.
All
Yeah,
right.
yeah,
See ya. Thanks. Bye
yeah.
bye.
Cool.